Welcome to qnawire.
Hello everyone, this is a solution to problem 13 of chapter 24 of college physics. In this problem, we're asked to define what the pulse time period and the pulse width mean in terms of radar technology. So basically, to answer this question, what we really have to know is how radar works. So what a radar does is at a specified period of time, it emits electromagnetic waves for a certain period of time. And so this is already telling us what we need to know, because the frequency at which the electromagnetic waves are emitted are related to the time pulse period, or the pulse time period. And so we have that this is given by t is related to 1 over the frequency at which the waves are emitted. And the pulse width is simply the amount of time it takes the equipment to actually get the waves to come out and then stop the waves from coming out. So during that time, there are a certain number of oscillations that happen, and this time that it takes to produce and then stop the wave is what the pulse width is. And so the next question is asking us how we can use these concepts to measure the range to different objects. So then, other than emitting these waves, what a radar does is observing the waves that are coming back reflected from objects that are at a certain distance. So during this time, the pulse that we've emitted is traveling twice the distance to the object. So it goes there, bounces back, and then comes back, and we detect it. So then there are a number of challenges that you have to face when you're doing this. Namely, if you have a really long pulse width, then you cannot detect objects that are in a certain range, because if the distance to the object is such that the first parts of the wavefront that you emit are coming back before the final parts or the ends of the wave that you emit or have left your equipment, then it's really challenging to measure accurately the distance to the object. And so the minimum distance that the object has to be away from your equipment is going to be twice the distance, is going to be the speed of the waves, which is just the speed of light, times the pulse width. And so rearranging this for the minimum distance is c times the pulse width divided by 2. So if your object is farther away than this, then you can accurately determine its position. Now, what about the frequency? What about the pulse time period? So again, here the challenge is that if your object is very far, then you might end up having shot out more waves than have come back. So if I just shoot at one pulse and I wait for it to come back, and then I shoot it out, and nothing comes back for me to detect before I send out the next wave, then I will never know whether the object was there to begin with or if it appeared later, for example. So you could imagine that there is, in place of this blob, this object, there's nothing there to begin with. But then the radar shoots out the waves, something comes in, and then suddenly something appears here. But by that time, the first wave has already gone over the position of this blob. So the first wave is somewhere over here, but the second wave is coming to hit this blob. And then after that, this electromagnetic wave that hit the blob is going to come back, and I'm going to detect it. But I won't be able to tell whether that is coming from somewhere over here, somewhere between my radar and the actual distance of this blob, or whether there was something farther down, farther away than this blob, and it is the first wave that got reflected, and that's what I'm observing, not the second. So this way, there's a maximum distance at which you can detect objects. And that is given by 2 times the distance to the object is going to have to be equal to the time period or time pulse period times the speed of light. You can also write this as speed of light over frequency because of this relation that we have here, that the period is just related to frequency with an inverse relation. And so rearranging this for d max, we find that the maximum distance at which you can accurately determine the range to an object is the speed of light divided by 2 times the frequency of the pulses. So what do you have to do if you want to measure objects closer to you? Then, as we've discussed, what you want to do is change the time or the pulse width of the radar. So you want to decrease this tau to as short as possible. So you want to make the bursts of electromagnetic waves, these things over here that you send out, to be as short as possible. This is going to allow you to decrease this distance. So you're decreasing tau, you're decreasing the distance. Well, what about the pulses? So if I want to maximize the distance, then what I have to do is make the period smaller, i.e. increase the frequency. And that way, if I, make the period longer, so that if I make the period longer, I make the frequency shorter, and I make the distance bigger. So f here in the denominator is decreasing, so that d max over here is increasing. So the idea behind this part is that if I can afford to wait longer for my pulse to come back before I'm sending out the next one, then I can accurately detect the first wave and every wave that comes back. So that is our answer over here.